of which, recording. Okay, so today's lecture is going to be a little bit lighter than normal. I know you guys have been working really hard, so we're going to have a little bit of a break. I'm just going to tell you guys about recursion today. We're going to give it a little bit more of a sort of rigorous treatment. So that's going to be the first part of the lecture. And then, I don't know, I just wasted 10 minutes. Maybe then I can give you a break. But in the second half of the lecture, I just have like 7 exercises that I want to do together, just so I can give you like more practical advice about how to program and help you understand like how I approach some of these problems. Because like a lot of the time when I've been talking with people and they're saying, oh, like this homework question's pretty difficult, and I say, have you thought about it this way? And then sort of light bulbs go off. So I guess the general philosophy here that like distinguishes us from the imperative approach is that in functional programming, the philosophy is like, given the input, what sequence of transformations on the input can I do so that the last transformation is like the thing that I want? Does that sort of make sense? So like for mode, for example. So this is how I thought about mode. For those of you who haven't done it yet, maybe I'll give you a little bit of a hint. So I'm asking you to find the most frequent character in a list, or most frequent element in a list. So I think, okay, if instead I had like a frequency list, like a list that just tells me like A occurred 3 times, B occurred once, then the problem becomes just find the maximum element in that list by the frequency and then return the character. Does that make sense? So then the question becomes, how do I turn the original list into a frequency list? But that's the philosophy, right? So it's like first transformation is into frequency list, second transformation is to grab the max out of it. So maybe you can think about it this way, right? It really has to be like a pipeline of functions where it goes in one function, out, gets another transformation, comes out, and so on and so forth. Instead of like looking at your input and trying to manipulate state. We don't have state. Well, that's what sort of monads are going to bring to the party. But at the moment, yeah, try to think of how to solve these problems by doing sequences of transforms. And the last transform should be the transformation into the answer. So if you haven't done mode, there's a little hint about how you could do mode. Okay, so the standard example for talking about recursion is factorial. It's maybe almost too easy. So let's just recall its definition. So the factorial, n factorial, is designated by this. N factorial is 1 when n is 0, and n factorial is n times n minus 1 otherwise. So there's a couple ways we can reason why the base case is 1. Like, why is the base case 1? Let's see if you learned anything from your assessment. What does n factorial representing combinatorially? Yeah. The number of permutations of a list of n objects. How many ways can you permute a list of 0 objects? 1. Right? So 0 factorial has to be 1. That's one way you can reason it from what its definition is. The other way that we can reason it is how we're going to reason in this class about recursion is we're going to set the base case to what it has to be in order for our recursion to work. And that's a totally fine way of doing it as well. And in fact, like, we could apply that here too. Like, well, what does n 0 factorial have to be? Well, I know 1 factorial is 1. No one's going to argue that. So if 1 factorial has to be equal to 1 times 0 factorial, that forces 0 factorial to be 1. Right? So another way of choosing base cases is just we're going to choose it so that our recursion works. So here's the obvious implementation for factorial if I were to ask you to do this. So sort of saying fact of 0 is 1, fact of n is n times fact of n minus 1. Now my question to you is, does this work? Is this going to satisfy typing? Yes? No? Yes? No. So there's one more nuance I just want to make you aware of, and it's a nuance arising from pattern matching on numbers. So you would think you'd be able to pattern match 0, but like 0 is polymorphic, right? 0 in our system, 0 can be an integer, an int, like a double, or a bunch of other stuff, right? So Haskell doesn't really know when you put a 0 there, like it's not really matching a string. So it's forced to do an equality check on that 0. So this is from the 2010 report. Matching a numeric, character, or string literal pattern k against the value v succeeds only if they're equal. So that's what Haskell's doing. So it forces you into an equality type. And so this is a little bit nuanced. So pattern matching on basically C types, like types that are built at the hardware level, we're not going to be able to pattern match against. So just be careful. Did you have a question?
Yes, so if you define it instead of non-written integer, then will it work?
I don't think so, but you can try. I honestly, I can't recall. I wouldn't think it would work because of this. Because like there's no, the integers are not defined like we do lists and stuff. Like I showed you how we defined a list and how we can just do a literal string matching with that. These integers, doubles, characters, like if we looked at them, they're defined at the C level, right underneath. And so the reporting about the equality is happening from C, like from the operating system. So we're unable to pattern match against. It has to do with the fact that, like I could set up integers in such a way where we like set them up as we have 0 and then the successor of 0 and then the successor of the successor of 1. But then like all arithmetic becomes, like to add two numbers would be a linear operation. And that would be very severe. I know we don't care about complexity, but geez, making addition a linear operation, that would really slow things down. So that's the answer. As soon as we break the abstraction barrier into like the operating system stuff, yeah, we can't really do pattern matching. So, these are really the last of the nuances. So just be extremely careful when dealing with these types of types. But we're going to be moving into like more of our custom data types, so this is going to become less relevant. I have a beautiful question for you guys to do in the next assignment. I coded it up last night. It was it's calculus, right? I'm going to show you like I'll show you how to take derivatives in like 2 lines, right? Okay, so no, we do have to derive an instance of the equality class for this to work. So I'm just going to add that indeed I need numbers that provide the equality. So here's fact of 0, we're going to get 1. So that's not doing a pattern match, but doing an honest to God equality. Fact of 3 is going to give us 6 as expected. What about this? Probably, yeah, but oh, okay, yeah. So it should be an error because stupid unary operator forgot to put a $sign there. So first there should be a $sign. So I think initially this is going to give you a typing error, but this is an infinite loop, right? Because it sort of skipped the base case, and now it's just going to loop forever downward. So we have a special name for this. This is called bottoming out, right? So you can think about it because we're going too far down. We're bottoming out. So this bottom symbol is used to refer to a sort of non-functioning functional program, right? One that sort of passes the type checker, but in its execution, like never stops. So calculations that bottom out will fall into these 2 categories: fails with errors or fails to terminate. So in this case, it fails to terminate. So we say fact of -1 bottoms out. I have to add those $signs. Okay, so how should we handle bottoming out then? Right? What are some options in general? Anyone have any suggestions? Huh? I can't hear you. Oh, Control C. No, I meant to say like.
You don't allow it, so you don't allow the input to be -1.
Well, how don't we allow it?
There's probably a condition thing.
Okay, but like, what's our response then? Okay, so yeah, raising an error would be one option. What's another option?
I was going to say that you put a conditional saying that if n is less than that, then you can throw an error, so print something of error.
Okay, but error is one of them, but like there's more options here, yeah. We can restrict the input somehow. I'm going to say, let's just call that precondition. I can say there's a precondition on this function. So you have to give me a positive input or it's not going to work. So that's another one. Any other ideas?
Absolute value and then take it off the absolution.
Well, but then you're reporting like factorial of -3 is 6, which is not mathematically correct. Yeah.
Just make it undefined, or is that?
Yeah, you can make it undefined. Anyways, here's sort of some options. We do nothing, right? Well, this is the Python approach, though. The Python approach is We're not going to check any input. We're not going to do any type checking. We're not going to prohibit the user from changing any variable, whether it be public or private or constant, right? Python just says, trust the user. Trust the user is going to use our functions properly, right? So I suppose this is a precondition. I just say, look, here's a function. Don't give it negative input or it's not going to work. Default output, right? I say something like, I don't know, if it's less, like we'll just call the factorial of a negative number 0. Right, because that doesn't make any sense for it, right? So I just say, look, we'll just designate some default output. So for this do nothing approach, debugging becomes hard, right? Because your program could work, but like give you garbage answers because you've like violated some preconditions silently. The default output is bad because it's like hiding errors, right? Like maybe it's better to know that you've passed factorial like a negative number rather than just sort of hiding it away. You can give an error message. I haven't really shown you error handling. I'll talk about error handling. But this is one that didn't come up that I was hoping. We could use maybe, right? The factorial can be a function which gives you maybe an integer, right? So maybe, remember, just depends this nothing data type. So we said undefined. Perhaps this is better than undefined because we can actually, if you hit an undefined condition in your Haskell code, it stops execution. Whereas if you hit nothing, you can pattern match against that. So that's another option. So each approach has its advantages and disadvantages. And like I can't say which one of these is right. I can just say each one has an advantage and a disadvantage. So for today, just to keep our function simple, and I think I'm going to do this on homework and stuff like that, we're just going to go with option, I'll usually do option 1. Right, I'll just say, look, just presume some preconditions. That's the simplest way to handle this. I guess for today, I'm going to say, let's just do a default output. That's okay for factorial because 0 is a nonsense value for factorial. So in order to ask if our input is less than 0, we now have to insist that our type is also ordered. So here's my new factorial function. If n is positive, then it's this, and otherwise just return 0. So this is the default value. So now fact of -1 gives us what? 0, right? Instead of bottoming out. So you can see that this is somehow an improvement. This won't work because I didn't put the $sign there or brackets. I need to fix the other slides. This will work. Okay, so this fact code is an example of primitive recursion. So there are different types of recursion that are going to be useful in like different scenarios. So any function that maps from the integers to the integers is defined by primitive recursion if the following 2 conditions are met. F of 0 is defined outright. And there was some confusion about this last year about what outright means. It means no more function calls, right? F of 0 is equal to this, right? You can't do more computation. And then F of n, for n greater than 0, is defined in terms of n and fn minus 1. So what does this kind of sound like? No. No, like, this is induction, isn't it? This is very almost identical to like the conditions of induction. Right? Induction says in order for Pn to be true in all cases, P naught has to be true and Pn has to be true. Right? So this basically is saying, okay, if you take an induction and you make it an algorithm, it's primitive recursive if it follows these 2 things. Now, note, like, more than integer functions can be primitive recursive. Like, this basically just means your input has to be countable and your output has to be countable. Do you know what that means, to be countable? It means like you're in a one-to-one correspondence with the integers. Like, I need to be able to like walk through the list. Like, so any data type which like you can list, right? You can make a primitive recursive algorithm. So you can't really make a primitive recursive algorithm over the reals. Yeah. No. You can replace integer with anything that's isomorphic with the integers. Yeah. Oh, sorry. By integer, I mean the positive integers. That's correct. Yeah, it's sort of irritating that we don't have a natural. Well, I can still count the integers, though.
They're countable, but in order to do induction, you have to each direction because it's n.
Yeah. No. Fair enough. Yeah. But here for primitive recursion, all I really need is an ordering. I'm not really utilizing the fact that 3 has to be bigger than 2. I'm just saying that f of n has to be reliant on like all the things that came before n in the ordering.
The other one's -1 doesn't.
Well, I can say 0, 1, like my ordering could be 0, 1, -1, 2, -2, 3, negative, right? That's an ordering of, right? And I can get everything I want out of that, right? So at that point I can say if this is f of 7, it has to rely on everything that's either plus minus 0 through 6, right? So like I know this, like I wouldn't do this for induction, but anyway, let's not get too pinned down by this. This is the sort of normal recursion that we're using, where we define a base case in like one inductive step. So more generally, we have a linear recursive definition, and linear recursive functions are called linear if at every step you only make one recursive call. Right, so this is mostly what, like factorial was linear recursive. Can you give me an example of something that isn't linear recursive? Yeah, Fibonacci numbers, right? The Fibonacci numbers make 2 calls, right? So you get this branching factor, and that really messes things up. Yes?
Finding the middle thing, like the mark, like you splitting lists and then kind of going to each half.
I guess that's how you, like, I suppose, yeah, you can implement mode so that it's not linear recursive, but you can implement mode so that it is linear recursive, yeah. Okay, so let's talk a little bit more about like how recursion works, like generally. So here's our fact code, and let's try evaluating it for n equals 4. So if you have fact of 4, this sort of becomes, or like expands to 4 times factorial of 3, which becomes 4 times 3 times the factorial of 2, which becomes 4 times 3 times 2 times the factorial of 1, which becomes 4 times 3 times 2 times 1 times the factorial of 0. Right? This is called the recursive stack. Surely you've heard of this before, but this is called the winding phase of the evaluation process, right? Where we're getting rid of all function calls, right? Where we get down to sort of some point where no more function calls are required. So during the winding phase, new activations build a stack of activation records. An activation is just an invocation of the function itself, right? So you start with some function, you activate, and then eventually all of your function calls disappear, or they like become the base case. It may make sense to write the above like in the opposite direction, so you actually get a stack. But since we're going to be reading this, it makes, in English we have to read top down, not bottom up. But if you want to conceptualize it as like building a stack up, you can conceptualize it as building a stack. Okay, so after winding, we do something called unwinding. And this returns from the activation stack, last in, first out. So I'm just going to, so fact4 winds, and we wind down to this point. And then this is how the unwinding works. So we start resolving these brackets, right? So fact of 0 becomes 1. And then that 1 times 1 becomes 2 times 1, becomes 3 times 2, becomes 6, becomes 24, right? So when we do these like sort of linear recursive functions, maybe in like Python or in C, like people complain, or you should have been complaining, that like this is super inefficient, right, to build all of these stacks up, right? That's really going to fill space. If we're not smart, a lot of our functional programs would just shit themselves in Python, right? Because you're not allocated that much stack allowance. What is this? Hold on, I think I'm missing a slide. Okay, well, I want to show you now how to like eliminate the winding phase. Right? Because if we can eliminate the winding phase, then we don't have to sort of be worried that we build this stack of invocations. So I'm going to define h factorial a little bit differently. I'm going to give it another variable. And here's a trick when you're coding, right? If you want to remember state, you can. Just store it in one of the input variables of your function. So that's precisely what I'm going to do here. I'm going to define another factorial function. I'm going to call it helper factorial. And I have to make a confession. This isn't the right way to write a function in Haskell. I'm supposed to be using camel casing here. But I just can't do it, right? For so long in my life, I've been defining helper functions like this. I'm just going to continue defining them like this. Because I think it's a little bit different than defining like properly a different function, right? So in my mind, when I write like h underscore, I'm like, this is a function that only exists to be called once by factorial. So this provides for me like a signal in my code, but I just need to be honest, that is technically not Haskellian. Okay, so the extra input that I'm going to give factorial, I was going to say, just use your first argument to store the answer to this computation. That sort of makes sense? So I'm saying if the factorial of 0 is just going to be answer, not 1 in this case. But I'm going to call h factorial from factorial with the starting answer as 1. So you think that we're going to call this and answer is going to be set to 1 at its first invocation. And then I'm going to say factorial of answer and n is equal to factorial of n times the answer and then recurse once. So see how this is going to work? It's going to keep like multiplying answer. And then eventually answer is going to be equal to n factorial. And it will then return in this case. So this is different than the factorial function we defined before, because this is what we call a Taylor recursive algorithm, and it's important. So this is how you define factorial via h factorial. Right? I'm just saying factorial, you're the helper factorial function, and start off the answer at 1, right? This type of base case. So if I call fact of 0, I get 1. Fact of 3 is going to be 6. And fact of negative 2 is bottoms out, because I didn't actually do any guarding against this. So for this one, we're doing blame the user approach. It just, I don't know, it keeps all of the messy details. We just push it off to the side. They're ugly, and I like blaming the user anyways. Okay, so let's take a look at what this means. So a function is called Taylor recursive or iterative if each execution of the function either is a base case, right? That is, it's defining the function outright. No more function calls. Not even to arithmetic. Arithmetic is a function call. Right? Your base case can't be like 7 divided by 2. It just really has to be a constant. And the function calls itself only with different values for arguments. That's literally the only two things that you can do, right? You can define a base case, or you can call the function again with different arguments. You can't have a function over that, right? Like we go back here, like look, that's all I did at this case step was call the function again with different inputs. I'm not allowed to do anything else. Yeah.
If you do h fact answer 0 equals answer plus 1, like as a base case, even though it doesn't work, but I'm just saying, does that satisfy Taylor recursion?
You want me to say h factorial answer 0
equals answer plus 1.
is plus a function call? Yes.
So that will not satisfy Taylor recursion.
Not my definition, because I said you can't, your base case cannot make function calls.
Okay.
And plus is a function call.
Yeah.
Okay. Okay, so let's look at the winding, unwinding phases of this function now. So I call fact to 4. That's going to call helper factorial 1 at 4. And then it's going to do this, right? And then it's going to be done. So there's no unwinding phase here. So we've eliminated like creating a recursive stack. See how that's a big, because like every function just totally just gets replaced by the next function call. Like there's no waiting that has to be done. I literally said fact of 4 is equal to this. So it doesn't have to build any type of recursive stack. Is this clear to everyone? Because this is important, right? So like remember, I'm not really trying to make you Haskell programmers, but trying to teach you how to use the functional tool set in Python and in C. So like this is a really great tool in Python and in C because you get to use recursion and you don't have to build a recursive stack. Okay, so that's great. So no unwinding required, no stack required. Okay, but there's a huge caveat here. So a caveat after this slide. So tail recursive algorithms are more efficient with respect to space, but a little bit more complicated because we have to use these auxiliary inputs to like store stuff and move stuff around. Tail recursion is also called iterative. This is basically a loop. Right? What I've shown you how to do is implement a while loop recursively. Last year, a lot of students found that this was like the way that they could do all their homework now. Right? That doesn't, like, I'm happy that that's not optimal, but good enough. Right? It's sufficient to be able to do all of your homework with tail recursion. Right? If that's all you left this class with and we're able to do that in Python, I'm totally satisfied with that. But I'll usually specify if I want you to do something tail recursively or not. Here's the big but, and I do not lie. In Haskell, this is default lazy evaluation, which is unusual. Most programming languages are eager. Have you ever heard this term, eager versus lazy? So like Python, C, those are eager. You ask a computation, it gets done immediately. In Haskell, it's lazy. Computations get done at the last possible instant. So let's see what this means about using tail recursions in Haskell. So fact 4 becomes this. Fact of, that should be helper factorial. So just in your mind, add all the h's. So this is the tail recursive factorial. So it does this, right? It's moving all of the stuff into the first argument, but it's not eagerly evaluated, right? All of those multiplications that are moving to the first arguments are being delayed. So actually, what happens after this? Python says there are no more function invocations. I now have to take my focus to that delayed computation that's sitting in my answer, right? So the squiggly braces are indicating delayed computation. Now the round braces are going to indicate the eager evaluations. And worse yet, we're going to do these eager evaluations outside in. So it's going to say, okay, evaluate this expression, which means you have to evaluate the lazy one inside, which means you have to evaluate that one, which means you have to evaluate this. And now you can unroll. So tail recursion in Haskell is a terrible idea, right? The system itself is designed to optimize against like primitive recursion. There's a lot of like compiler optimizations. So like one of the use cases of Haskell is if you really do find a clever way of defining your problem recursively, the compiler is able to do like a crazy amount of optimization in like how it computes all of your recursive functions. So we're not engaging with any of that type of stuff in this class, but you should know that like, there are some genuine use cases for using Haskell. So just, NASA got a little bit irritated with me for not specifying this last year, but yeah, doing tail recursion in Haskell is kind of unnatural. But again, I'm not trying to make you Haskell programmers, but functional programmers in your normal tools. So this is not something that you really have to remember. I just want to mention it once. There is a great Stack Exchange discussion about this that I'll post at the EdStem that you could read through if you want. That really explains how Haskell is able to optimize against this. Like for instance, the compiler will look at this type of expression and like come up with clever ways of resolving the lazy evaluation with like divide and conquer methods and stuff like that. This doesn't necessarily have to be a linear rollout. Okay, so suppose now that like we write some Haskell code and we want to prove that Haskell code actually is producing what we want it to produce. You should have taken another course. It's either you taken it already or it's happening concurrently, where you had to prove the validity of your code using like loop invariants and stuff like that. No? Okay, well, some of you have taken a course where have you ever heard the term loop invariant? No? Oh, okay, then never mind. Okay, so suppose we want to prove that the Haskell code we wrote is actually correct. So for primitive recursion functions, this is easy, because I said primitive recursion is basically just doing induction. So very quickly, I'm just going to show you how, and this is going to seem very silly, because this is a very trivial example, but suffice to say for like more non-trivial examples, this may be more difficult, but I want to prove that factorial of n is equal to n factorial. Now, this is a strange expression, right? Because I'm saying like the invocation of this Haskell function is going to equal some mathematical expression, right? That's why I tried using like the TT font on the left-hand side and like the script font on the right. But this is totally fine to say. Like I'm asserting that I've written a function that has implemented this mathematical construct. Okay, so I say, that's my thing I want to prove for this. So I want to prove this function actually returns n factorial. So as with any proof, I have to start by stating the thing that I want to prove. So my proposition at n is if and only if factorial of n is equal to n factorial. I know that seems really sort of circular logic, but again, like there is sort of, we know what the right-hand side is. It has a definition. Okay, so this is a little bit weird now because like Pn is an equation. So I'm gonna prove that the left-hand side of P naught is equal to the right-hand side of P naught. So the left-hand side of P naught is factorial of 0, which is equal to 1 by definition, which is equal to 0 factorial by definition, which is equal to the right-hand side of P naught by definition, and therefore P naught. Well, the base case should always have like a totally trivial explanation. It's usually going to be by definition, by definition, by definition, by definition, by definition. Okay, so P naught is true. Here's my induction hypothesis. I'm going to assume that, yes, my factorial function at n indeed does return n factorial. So now I need to prove that Pn plus 1 is true. So what is the left-hand side of Pn plus 1? That's the factorial of n plus 1. It unwraps to this, right, n plus 1 times factorial of n plus 1 minus 1. So this is by definition, but in particular, it's line 3 of my function. Right? If we go back to the last slide, like those two things are literally equal. Right? That's why I'm able to make this deduction. Okay, so here I'm saying n plus 1 minus 1 is n. Right? But technically, that would require a little bit of explanation. But I'm comfortable with just saying this. Like, I am taking for granted that n plus 1 minus 1 is equal to n. Right? This seems like too trivial to like go and conduct a proof on. So you can use this as well. Right? Just be careful, because if you take something for granted which is not like totally obvious, then you may get dinged. And if you leave this out, I may ding you too. Like, I want you to make all of your assumptions very obvious, right? So you can say, look, I'm just taking a very simple thing for granted. Okay, but by our induction hypothesis, this is equal to n factorial, which means that, so this is a little bit weird. This is the slice n plus 1 times, and this is me applying that slice, right? So we get n plus 1 times n factorial, that's one application, which is equal to n plus 1 factorial by definition. Right, so this is equal to the right-hand side of Pn plus 1, and therefore Pn plus 1, and therefore conclude. Right, so very, like, almost overly trivial, but I've given an inductive proof that, like, what my Pascal program is doing is, in fact, calculating what I expected it to calculate. Yes, sir?
Could you explain the difference between by and IH in the application step?
So I'm saying this step is by the induction hypothesis, because I'm replacing factorial of n with n factorial, which is indeed the thing I'm trying to prove, right? Right, so that's why I'm saying this is by the induction hypothesis.
That's fine, but why did you have to specify application?
Because this is a slice. The n plus 1 times is a function call. Yeah. So I'm saying I'm applying that function call. Okay. And now it becomes n plus 1 times n factorial.
So you're mixing kind of card and math.
Yes, and I know it's going to be kind of, it seems unnatural, but that's what it's like, right? So if you take a look at my doctoral dissertation, every piece of code that I wrote comes also with the proof that it's returning what it's supposed to do. There are places where this is like necessary. You don't want like a braking system that sometimes works, or like cancer diagnosis that were like mostly correct, right? So I have lots of friends in medical diagnostic verification, right? That the algorithms that they're writing like are actually provably producing the results that we expect. You may not think of that there are some very high stakes places where code could be implemented. Like, you better be sure that everything NASA sent up in their first spaceship was verified till the cows came home, right? You don't want to like launch 3 guys into space and then find out there's a misplaced semicolon, right? That crashes the whole International Space Station. Could happen. Yeah, I'm not actually sure that that's a true story or if that's just somehow.
But because of like the 2032 problem.
What I recall is that there is a satellite that failed to launch because there were 2 groups working on it, and the one group was working in imperial and the other group was working in metric. And due to that. Okay, so is it true, or is that just like an urban legend? It just seems to me implausible that like probably a multi-billion-dollar project failed over something so simple. Did you look it up? Oh, okay. Someone can look it up and tell me if that's actually true or not. It just seems like something that would be an urban legend, like too nonsensical to actually occur. But in any case, so for correctness checking, a tail recursive algorithm. Okay, so now I'm going to teach you how to verify tail recursive algorithms. right? And I'm going to have you do this a lot, right? Because this is a really good exercise to write a Taylor recursive algorithm and then prove that your Taylor recursive algorithm is correct, because usually proving it is the thing that helps you define it in the first place. So for correctness checking a Taylor recursive algorithm, we need something called an iteration invariant or loop invariant. This is a condition or property of the algorithm that must be true regardless of what level of winding we are at. It is usually some assertion of how the parameters are combined to produce the desired answer. So remember, I wrote like a Taylor recursive factorial example, and like all we're allowed to do is call the function on different input. Therefore, the input has to be, like, it must be the case that we can combine the inputs somehow to like get the answer. And that must be like an invariant property at every call. So this is more clear with an example. So can anyone guess what the iteration invariant is for the factorial tail recursive function? How can I combine the input somehow so that like no matter where I evaluate the iteration invariance in this code, it's always going to come up true? And maybe I'm asking too much. I'm going to show you it, because like I think once you see one example, then it sort of clicks. At any given point, helper factorial at answer n is equal to the answer times n factorial. Does that make sense? Okay, so now I'm going to go through that function and show that at every point in that function, that invariant holds. Okay, so there's a reminder. There's the two lines. So we must now show that at each line, the following iteration invariant holds. H factorial of answer in n is answer times n factorial. Left-hand side of 1. So helper factorial of answer in 0, according to our iteration invariant, should be equal to answer times 0 factorial, which is answer times 1, which is answer. Yes? Right-hand side of line 1 is answer. Okay, so therefore left-hand side of 1 and right-hand side of 1 are equal. So we've shown the equality at line 1. Agree? Cool. Left-hand side of line 2. So I'm saying helper factorial of answer at n is equal to answer times n factorial. Okay, nothing really else to do here. Right-hand side of line 2. Helper factorial of n times answer, n minus 1, according to our iteration invariant, is equal to n times answer times n minus 1 factorial. But that's itself equal to answer times n factorial by definition. So therefore, left-hand side of line 2 is equal to right-hand side of line 2. Does that make sense? I see some squiggles. So you got to tell me what doesn't make sense.
Maybe go through that. Yeah.
So I'm saying h factorial of answer in n is equal to this invariant, right? So that is this. Right, I'm saying it's like the first argument times the second argument factorial. So this is the first argument times the second argument factorial. Like I'm just saying what this is equal to according to my invariant. And that comes out. And that just simplifies to answer times n factorial. So here the left-hand side of 2 is equal to the right-hand side of 2.
So it's just another flavor of inductive proof.
Yeah, a little bit simpler, right? Because we're not really assuming that like anything is working. Like I'm saying that like no matter where you're calling this, like this function is going to have this property, right? Because all a tail recursive function does is invoke itself. Like nothing else happens. So like as soon as I go and verify all of this, I can conclude, yeah, at any given step, right? The combination of the arguments is going to construct the answer in the following way.
But we are taking for granted that answer times like n factorial. Like in the second step of right-hand side of step line 2, we are.
What, this?
Yeah.
Because like, that's why I switched colors here. Like we've moved from out of Haskell into the world of like arithmetic. So like you're going to do a tail recursive function for reversing a list in tutorial, and the iteration invariant, you're going to say something like reverse this list. So I guess that's what you mean inductively. Yeah, I agree with you then, right? Sort of the thing that we're saying it's equal to is sort of presuming that it works somehow. Yeah, I see where you're coming from. Okay. So thus our iteration invariant is correct, and thereby I can conclude what? That factorial of n, which is equal to the helper factorial of 1 at n, by our iteration invariant is going to be equal to 1 times n factorial, which is equal to n factorial. So I've just proven that, like, if I define factorial n tail recursively, it is in fact giving you what we expect it to give. Right, I have another example after this. Unfortunately, it's arithmetic again, but anyways, to finish this though, so we sorted correctness, but we also have to, in order to be an algorithm, we have to also prove that this thing terminates. So how can we prove that this terminates? To prove a tail recursive algorithm halts, we need to find a bound value depending on n, which is always non-negative and decreasing at every recursive call. So that means I just have to say every invocation of my every invocation of my tail recursive algorithm should be bounded by something, and that something should be like monotonically decreasing until it hits 0. So this gives an upper bound to the number of recursive calls before a program can terminate. So again, I'm insisting on decreasing, 3, 2, 1, and not the weaker non-increasing, which could stay static. So does anyone have an idea of what the bound value of this could be? So you basically look at this, and I said, well, what is this bounded by? What is the number of iterations of this bounded by? Yes. Okay, so I say the bound variable for this function invocation is n. This is not going to invoke itself more than n times. Okay, but I can't just sort of assert that. I have to prove that. So here's my proof. So notice by our presumption, we had a precondition. N always has to be non-negative. I was never allowed to give factorial a negative number to begin with. Okay, so that satisfies the first condition, that n is non-negative. And now I'm just going to show that the bound variable of this is greater than the bound variable of this. So the bound variable of this is n, as you stated, and the bound variable of this is n minus 1, right? We're saying it's bound by its second argument. And n minus 1 is strictly less than n, and thus the bound value decreases at every recursive call. Right, so we've proved correctness and we've proved termination. So our Haskell code is now certified, working, right? Providing our proof doesn't contain errors in it, but other mathematicians certify it. So that's neat, I think, that we can write a piece of Haskell code and we can actually write like a mathematical proof asserting that it's absolutely calculating what we expect it to calculate. Yes. Well, I was restricting us to integers, so we're not going to get a half, right? So don't forget that, you have to put preconditions in for some of this stuff to work, because of course this is not going to work on floats. Yeah. Okay, so consider the primitive recursive definition of exponentiation on naturals in Haskell. So I want to take the power, I want to do x to the power of y, where y is not allowed to be negative. That's going to be a precondition. Can we give a tail recursive version of this algorithm? The answer is yes, but okay, so let's go. And so h power, so that's so I want to take an integer to an integer to an integer to an integer, right? This is going to be the first argument, right? This is where we're going to store the answer to the computation. So this is hpow of answer x to the power of y. And then we're going to have another line here, hpow answer xy is equal to. Okay, so what's the base case then for this? Or maybe we should step back, right? If I'm going to define power, which is integer to integer to integer, what should power be equal to? I'm going to call hpow, but what initial argument should I give it? 1. Yeah, I don't think I make it 0, or that's real. Because remember, we're going to take answer, and we're going to repeatedly multiply it by stuff. So the identity for that is going to be 1. Okay. So what should this be? Or what? Okay, so yeah, what should I put here for our base case? Yeah, so this is going to be 0.
Which way you do it? You get
X to the power of y. Yeah.
So y is 0.
Y is 0, yep. And then I don't care about what this is. Well, I can put x here if you want, but what's answer? Okay.
We
Now,
don't need X.
okay, yes, we don't need X there. Okay, so all I'm allowed to do now is call helper power with different arguments. I'm not allowed to do anything else. So what should I do now? Right? Yeah, H power answer times X, X, Y minus 1. Okay. Oh, integer. Load foo. Oh, that's in a, sorry, that's defined here. Okay. Okay, so let's check. H pow 2 cubed. Oops, sorry, yeah, pow. 8. 27. Okay, so that seems to be working. So here is the implementation that I just did over on the other side. What's the iteration invariant? What is true? Right, what can I set? Like, what is H pow answer x n equal to invariantly? Like, how do I combine the arguments to get the answer? Yes, sir. Answer times x to the power of n. So yeah, this may seem a little bit unnatural because, like again, as my dear colleague over there said, we're using the thing that we're implementing in this, but like this is a known quantity xn. You can even use like English statements here too, like which is sometimes appropriate to say, look, I'm just going to reverse the list. You'll see that in your tutorial this week. Okay, so note it is fine and indeed the point that the right-hand side of the iteration invariant uses a function power that we presume is working, right? In fact, sort of starting backwards is almost like the way to go. Like you want to start with your iteration invariant and then build the function, right? This is really informative, right? Because you know what your your target is going to be. Okay, so we're calling the definition of hpow being this. We must show that at each line the following iteration invariant holds. I need to show that hpow answer xn is equal to answer times x to the power of n. So left-hand side of line 1, h power answer x0, according to our iteration invariant, should be equal to answer times x to the power of 0, which is equal to answer times 1, which is equal to answer. Right-hand side of line 1 is answer, and answer is equal to answer, so good. We've proven we've proven line 1. Left-hand side of line 2, h pow answer xn is equal to answer times x to the power of n. Not much more we can do now. Right-hand side of line 2, h power is of answer times x, xn minus 1 is equal to, according to our iteration invariant, answer times x to the n minus 1, which is equal to answer times x to the n, just according to the rules of arithmetic. Left-hand side of line 2 is equal to right-hand side of line 2, and thus our iteration invariant is correct, and thereby we can conclude power of x to the power of n, which is equal to this tail recursive h power at 1xn is equal to, according to our iteration invariant, 1 times x to the n, which is equal to x to the n. So there you go. Then we've now proved correctness of our power function. Yes, sir. Sure. Okay, so remember, I'm just applying this rule to here. Okay, so this rule says that answer goes there. So answer times x goes there. And then this part becomes this. So this part becomes this. That's just according to what we said. We're just evaluating the right-hand side of that function according to what we said the invariant was. And it turns out, when we do it and we simplify, we've proven that they're equal. Does that sort of sort things? Yeah, okay. Now, it just suffices to show that we get termination. So what is the bound variable in this case? It should be very clear, right? The exponent itself. So the bound variable is non-negative, firstly, because of our precondition. I said you can't give me a negative input. The bound variable of the tail recursive power function is going to be n, which is equal to n, which is strictly greater than the bound variable of the recursive call, right? Because this has gone down 1, so this is n minus 1, which is strictly less than n. So therefore, our bound value is strictly decreasing. It's strictly decreasing. It can never be negative, so therefore it has to stop. We conclude that our tail recursion terminates. Mutual recursion. Here's one extra type of recursion before we get to the second part of class where I'm going to, we're just going to go through a bunch of examples. So mutual recursion is when two or more functions are defined recursively in terms of one another. So this may be unusual. So here's an example. I can define even and odd in the following way. Even of 0 is true, and n is even if n minus 1 is odd. And I can define odd like this. Odd of 0 is false, and n is odd if n minus 1 is even. Yeah. Yeah, mutually. Yeah. These functions have defined themselves mutually with one another. Seems a little bit weird, but this is totally logically consistent. If you can put it in Haskell and it's going to work, it's just going to keep jumping in between. Right? It's sort of like 7 is odd if 6 is even, if 5 is odd, if 4 is even, if 3 is odd. It's like a dumb way of doing this, right? The better way would just be to check its division mod 2, but it's illustrative. Oh, so I did do a trace. So even 4 is odd 3, is even 2, is odd 1, even 0. So keep this in mind that it's totally fine to presume your functions are working and use them mutually, which is going to be something that you're going to have to do in your next assessment, which is going to be deployed next week. And again, there's a beautiful problem in it that I can't wait to give you. Exercise. You use mutual recursion to extract the even or odd positions of a list. So there's any ideas of how we can do this? It's going to be very similar, right? So so this is sort of, maybe we could argue about these base cases, but in any case, so the evens, am I doing this? Why am I pulling up? Is this backwards? I think this might be backwards, right? Because this is the first position, right? So the first position is at an odd position. I think I've swapped evens and odds here. Right, because the fact that I'm keeping the first position, yeah, I think this is backwards. Okay, well, let's just try to program it in here. Evens, odds. Okay, so I want to take a list, integer, and I want to return an integer list of the evens. And odds, I want to return and take an integer list and return an integer. Okay, so one of these two shouldn't have the empty base case. And I think that's odd. So evens, because 0 is an even position, right?
That's the question. Are we assuming the first thing is an even position or an odd position?
Well, the first thing's at position 1. 1's odd. So that's an odd position. Right? So therefore, odd can't have definition at, right? This has to be undefined, I believe. Right? So therefore, what should be the base case of odds? Like the singleton list, right? Right, that's the first list that has an odd position is a list with one element in it. Okay, so then if I want the evens of this, then I dump the first x, and then I want the odds of x's, I believe. And then if I want the odds of this, I keep x, and then I get the evens of x's. Oh, odds. Thank you. Let's see. Evens, 1, 2, 3. That should be what? 2? That's exactly what I wanted. Anyone see my mistake? No, I'm talking about like the positions. So the even positions are 0, 2, 4, 6, 8. And the odd positions are 1, 3, 5, and so on. There must be a very simple mistake that I've made here. So let's just trace this. If I give this 1, 2, if I give evens 1, 2, then x becomes 1, x becomes 2, and I want odds of singleton 2. That should have returned 2. Okay, hold on. Let me go back 1. Ugh. Okay, so that's fine. Well, how come this is not fine? Let's see if the chat knows. Chat? Nope. Hmm?
Oh, you needed to find singleton evens.
No, evens for a singleton list goes to odds.
Yeah.
for an empty list.
I'm a little bit flummoxed here.
Maybe it's the definition of undefined. Odds emptiness. So you're hitting
Evens of the singleton list goes to odds of an empty list.
Oh, that's true.
So should that be the case for evens on a singleton list?
Yeah, maybe I need to add one more base case. Maybe you're right, that this is this, right?
yes.
Okay, let's check. Okay. Perfect. Okay, let's get odds. Okay, perfect. Thanks for that. Thanks for that. I told you you may have to help me today. Okay, so obviously I'll correct those slides. I'll see what I was trying to think there. Okay, so that's the last one there. I think we should just keep forging forward because I was having those technical difficulties, even though I need to rest my voice. Okay, so now we're just going to do like a ton of recursion problems. I'm going to give you a way to like think about writing programs recursively. Like I'm going to try to give you practical advice. Okay, so obligatory meme, right? Recursion, it recurs, and so on and so forth. Okay, so this is from Hutton's book, and he lays out the following sort of guidance. So Hutton, like, this is a professor who actually teaches functional programming to first years at his university, but they go through it like a lot more slowly, and like we're going to do so his book is broken into like two pieces, like what he teaches to his first years and then like all the advanced stuff. And like we're going to definitely do all the advanced stuff, so don't feel too bad. But he's sort of like the godfather of functional programming. You should check out his book. I think it's in the library, and it's not very expensive. So the first thing that we want to do when we define any function is define the type. Right? That's what we've been doing this whole time. So step 1, define the type. Step 2, enumerate the cases. So consider the function's domain. Right? So since we've defined the type, we know what the domain is, and that domain should have boundaries, should have edges. Right? So if it was the positive naturals, we may have an edge 0. If it was lists, we would certainly have an edge empty. Okay? Define the base cases. Okay, so for every edge case that we've delineated, we're going to have to like specify what happens on that edge case. Define the inductive cases. So like the principle of mathematical induction, determine how to deduce the answer, assuming that your function is already returning the answer on some type of smaller input. This has always been the name of the game. I've been screaming at you guys. Just assume it's working. Right? Assume your function is working on smaller input and ask yourself, how can I use that to construct the answer at this level? And then generalize. Right? So I'm going to teach you a lot of higher ordered patterns soon. So you should always have like a refactoring on your code. So sometimes it is better to define the inductive cases first in order to define the values of the base cases. So it doesn't necessarily have to be in this order, right? Because it may not, as I was saying, sometimes like the base cases aren't going to be obvious. And like don't get cranky with me like next assessment. I'm not going to tell you what the base cases are. In this class, it's like up to you to deduce what the most sensible base cases are. I know you're being used to being told what the edge cases should be, but that is like a central part of like designing functional programs. So that's up to you. I did a little favor this assessment because the only public test for permute is the base case. And I've already saved a bunch of people from getting the base case wrong, right? Because I'm saying this should have been the list of the empty list. So really the base case has become the only place ever where it's like possible to lose marks. Because once it's working inductively, it works on all cases. Okay, so let's apply these steps to create product, a function that takes the product of a list. what did I mean by product of a list? Oh, so given a list, I want you to multiply all the numbers in the list. So define the type. Okay, so type is list of integers, and I want to return an integer. What are the edge cases here? So like our domain is integer lists. What are the edges of that domain? Yeah, empty list. Anything else? Possibly singleton list, but I don't know. Maybe if I don't think so. So it seems that the edge of this is going to be the empty case. So I'm just going to say, okay, so I'm going to have to define product on the empty list. I'm going to have to define product in the general case. So I'm just like building up the framework. Define the inductive case. Okay, so this is sort of like the point of functional programming. This is maybe the step that people get confused by. Presume product is working on smaller lists. That is to say, assume product is working on x's. So if I can get the product of the tail of the list, what remains to do? Yeah, multiply the product of the tail by the head. Okay. So now all we have to do is like work out what our base case is. So what should product of empty set be? Why?
Multiplied by 1x. So if it's multiplied by 0, it just gets 0 and multiplied by the multiplicative identity.
Okay, yeah. Yes. So I'm just going to re-explain what you said. That was great. That was perfect. So what I said is, so suppose we didn't know the product of the empty list was 1, or suppose you want to be convinced that the product of the empty list is 1. This is your strategy. Look at the next one up. Like look at any function call that is going to call the base case, right? So I'm saying, let's look at the product of the singleton list x. I don't think anyone is going to argue that the product of a list of one element should be that element itself. That's sort of like more easily digestible somehow, yeah? Okay, so if I know that the product of the singleton list by our definition has to be equal to x times the product of the empty list, what can we deduce? Yeah, that x times product of list is equal to x, and therefore product of the empty list has to equal 1. Does everyone get that? Because you're going to need to do this, right? So, and again, so the strategy is this, right? Get your induction working, which you're not going to be able to, in like practically speaking, but you should be able to define it somehow. And then look at the first case that's above the base case. That is going to make a call into the base case. And that base case is going to have to, you know what it has to return in order to make that current step work. Right? So that is how you define base cases. We define base cases so that our recursions work. And like this is the answer to like a bunch of stuff in math that may not make sense. Like why is x to the power of 0 1? Because that's what we need it to be for the recursion to work. I know that's a really unsatisfying answer maybe, but that really is the answer. Same reason the sum of the empty list is 0, right? Because it needs to be that for the base case to work. Okay, so let's do a couple of the prelude functions. Like these exist, but let's just like utilize this method to try to define them. Define the prelude function drop, which gives, given a list and a number, removes that number of elements from the front of the list. Okay, so what is the first step of Hutton's prescription? Define the type. So what is the type of this?
List to integer to list.
List. Sure. I just permuted the first two inputs. Doesn't really. What you said would have also been correct. So actually, I think this is wrong. I think you're more correct because I said given a list and a number. So that sort of implies that the list would be the first argument. So I'll make that change. So this one just takes the integer and it doesn't really matter, but I should be more careful when I write these things. Okay, so here's the type. What are the, okay, so now we have two inputs, right? So we're going to have like this sort of multiplicative effect of base cases, right? Because there's going to be, so the domain now is sort of like the Cartesian product of the integers and the lists. Okay, so what are the edges of the integers in this case? So first of all, we're probably going to have a precondition, right? You can't drop a negative number from a list. So first we'll say, okay, it's not really int, it's positive ints. Okay, so what are the edges of the positive ints? Or I suppose non-negative ints, right? Okay, so there's at least one base case for the integer 0. The second position is the list. What is the edge case for the list? Empty. Okay, so we're going to have to worry about all combinations of those things, right? It has to be 0 and empty list, 0 and non-empty list, non-zero empty list. Although perhaps I could get rid of one of these, but you can always simplify after. Right? So, but be careful, right? If you have like multiple inputs, you have to consider all combinations of those edges somehow.
What would happen if you dropped the line at 5?
If I dropped 5,
Like which?
I'm not sure I could drop any of these. I'm not sure. So if we drop 5, then 6 would break because there's no.
There's no stopping of the 0.
No. It would go down to here. It would become, because this can't accept empty lists. Right? This presumes that this is at least has one element. So if I didn't have this and you call drop empty, it would go to here. And I'm sure here that when we define what it means to drop on n, it's not going to make sense that n is 0. So like it's going to be pretty obvious what it means to drop n elements of a list means, right? Drop n x's is going to be drop n minus 1 from what remains. So we'll probably have to have a case where the drop at our inductive step, that n has to not be 0 in order for that to work. Because I'm never going to be able to say, we're going to be prohibited for calling drop with negative numbers. So again, it's best to like have more base cases than necessary and then eliminate them once it's working. Okay, but I can't see any other edge cases in this case. So what's the general case then? So we have our typing information, we've delineated our edge cases. What should the general case be? Right, so like how do we drop n on, right, sort of a non-empty list, right, a tail and head? Okay, so let's define the obvious edge cases then. So I guess this just shows the answer. If I want to drop 0 elements from the empty list, that's fine. You get the empty list back. If I want to drop 0 things from a non-empty list, you just get the non-empty list back. If I want to drop n elements from the empty list, you get empty list back. So that seems to be fine. Disagree?
Could you simplify line 5 to just like drop 0 x's and then just return x's and then maybe?
Yeah, actually, I should have just put, well, I suppose because this will catch the empty list first. Like what I'm trying to say here is that like this list is definitely non-empty, but in fact the pattern matching had already, like if we got to line 5, that means we did not trigger line 4, which means at line 5 I can, but maybe I could have just, yeah, I think what you mean to say is I can drop line 4. Yeah, it seems to be that I could probably drop line 4. But again, worry about simplifying after the fact, right? Because once you'll get this working, and then you can start removing lines one by one to see if it continues working. Right? So remember, this is like practical strategies for like implementing functional programming. So it's okay that they get bloated and then we call them a bit. Yeah.
It's a question of which one hits first, which base case hits first, whether it's 0 empty list or 0 x's, right?
Well, it's in order, right? So if you give me drop 0 empty, it's going to trigger at line 4, not line 5, because line 4 occurs.
In terms of its like steps into the recursion, like which one it will hit first, which base case it will hit. So if it doesn't satisfy 0 empty list, then it will go to 0 x's.
Yeah, but I think what was saying is that like case 4 is actually a subset of case 5.
Yeah.
And I'm saying I agree, right? But like we can do that at the end, right? We can do that in part of our simplification. So let's do the base case, or let's do the inductive case, right? So we presume drop is already working. And now I can say drop n elements from x's is the same as dropping n minus 1 elements from x's. And then we should be off to the races, right? So now we can go back and try to simplify some of this. And I think you're certainly right that line 4 wasn't necessary. But I do emphasize that it's better to have it there and then remove it. Because in our way, we're going to have a bloated working implementation that we can call. Whereas if you missed base cases, it's going to be a lot harder to fix that. Define, so I'm going to skip this one because it's very similar. So this is removing the last element. This is also a prelude function, but it works very similarly. It's a list to list. The edges, maybe this isn't. Okay, we'll go through it. So define the prelude function initial, which removes the last element from a non-empty list. Okay, so now what's the type? Takes a list and returns a list. What's the edge case here? Singleton list, right? Because now that we've specified in our precondition that the list has to be non-empty, empty can't be the edge case because that's excluded from the domain. So now the domain, actually the edges are, and there's an infinite number of edges here now, because there's an infinite number of singleton lists, or at least theoretically infinite. Well, there's one empty list for every integer that we're able to represent, right? So there's the edge. Is there any other edges? Not that I can think of. Like if I want to remove the last element from something, I need the list to be at least one element long. Doesn't seem to be like any other edges. So what's the general case? Well, that's just what happens in xcons x's. So define the obvious edges. So what does it mean to remove the last element from the singleton list? Well, it just is this. Presume init already works on shorter lists. So what does it mean to remove the last element from xcon x's? Well, that's like keep the first element and then concatenate with the initial of the rest. I should have used the cons operator here, actually, now that we have the cons operator. But it's equivalent. So, but nothing really. But it's just better to stick with one. Like when we concatenate a scalar with a list, it's best to use cons. Like that's precisely what that operator is for connecting a scalar with the list. Whereas the concatenation operator is for connecting a list with the list. So I actually took the first element, made it a list, and then used the cat. It's just doing one. It's more sophisticated than it needs to be, right?
But doesn't init give us a list? So
Yeah, I can always connect a scalar with a list, right? I'm saying it should be x colon init initializer of x. That's the same thing as here, right? Yeah. Oh, that's better, right? Okay, great. But both are equivalent. But you should strive to do things the same, so it's easier to debug.
it's better to do concat reverse to get it on the other end than to do I did that in my assignment.
That's fine. For your assignments, you should have the philosophy, if it works, it works, right? I'll show you my elegant solutions afterwards. You're gonna go, but if it works, it works. At the first assignment, I was expecting struggling, right? Because it's tough to get familiar with the functional paradigm, because it's mostly you clinging on to everything that you know and letting go of it slowly. Whereas I think by assignment 2, you'll know that the imperative approach is just not gonna cut it. Multiplication, using only addition, give a recursive definition for multiplication on non-negative integers. Pretend also that we sort of don't know that 0 times a number is a number. We're gonna have to work that out. Why should 0 times a number be 0? Anyone ever think about that? I suppose we can say multiplication is n times x is n copies of x. So 0 times x is having 0 copies of x. But we'll deduce it. We'll sort of come up with a way of deducing that x times 0 should be 0. Okay, type. So non-negative integers, what should the type of multiplication be? Yeah, int to int to int. But we just say with the precondition that we're not allowed to have negative input in the first 2 positions. It would be really great if Haskell had a positive integer type. We can work it into, maybe that's not a bad assignment question actually. Right? Create a custom data type for working with positive integers. But in any case, so here's the type. What are the edge cases then? If I'm saying that the inputs have to be positive. Yeah, so it seems sensible that I need to specify what happens at either edge. I need to know what multiplication of 0 and something is, and what something in 0 is. We know it's 0, but like let's deduce it instead. What about the inductive case? Like what do we do, or what's the, like what are the other general cases here? And there's going to be more than one, right? That's why I chose this. This has 2 inputs. Pardon me? You're saying 1? So we need to do, yeah, but we sort of have to like decompose it a bit. Or maybe, okay, no, I changed my mind. You're correct. Let's do it like this. Because, sorry, you can't pattern match on, this really irritates me because I want to pattern match on the successor of x, but it doesn't let you because of the stupid way that integers work in the system. Okay, so that is correct. So there's our general case. Multiply x by y. So let's start going through these things. So supposing like the edge case is not obvious, let's just skip it for the time being. What should the inductive case for multiplication be? Well, let's just say the multiplication of x and y should be equal to, and remember, I'm saying we're restricting ourselves to addition to define multiplication, should be x plus the multiplication of x and y minus 1. You could have done it the other way. We basically have to reduce one of the inputs by 1. It has to go down by 1. So everyone agree with sort of this inductive case? Okay, so now we should be able to deduce what the base cases are from going 1 above the base case. So what is 1 above the base case? Multiplying something by 1. So we know that multiplying x by 1 should be x. So that means that when I call x and 1, I'm going to get x plus the multiplication of x and 0. So if I know that x should be equal to this, what can we deduce about the multiplication of x and 0? It's 0. And that's how you get your base cases. Okay? So like, I know these are trivial examples, right? But it's going to be the same philosophy when I give you something like less trivial. If you're having problems like deducing what the base case should be, just set it to what it has to be set to in order to make your induction work. And there's not going to be multiple ways of doing that, right? If your induction is correct, there should be like one thing that the base case has to be, right, to set it to. Let's do another one. The power set of A, denoted by script PA, is the collection of all subsets of A. So power set of A is equal to every set A such that A is a subset of A. For example, all the subsets of 1, 2, it's the empty set comprised of 1, set comprised of 2, and the whole set. Letting list represent sets, right? Because we don't really have we do, but I don't want to call in custom data. Define power set, which gives us the power set of a list. So this is very similar to what? Permutations, right? This is extremely similar to permutations. So let's go through it, right? So what's the type of this power set operation? Okay, it takes a list of integers and returns list of int. Or did I say integers here? I didn't say integers. I said collection. Okay, so list of A returns list of A. Find the edges. Empty list, yeah. General case. Well, the power set is usually like how you're going to decompose the input somehow. Yeah, it's going to be, okay, so this is going to be our general case. Asking how I'm going to call power set on if I remove the first element. Actually, I should have called this x's and then double x's here. Because x here, the head of this list is going to be a list. Oh, no. Sorry. No, the input is a list. This is correct. Okay, so let's go through it. So what are the power sets of the empty set? Yeah, list of empty sets. So be careful with this one. Perhaps this is one we could have worked out backwards if we were like getting stuck here. Presume power set already works on shorter lists. How do we get the power set here? So we have power set x cons x's. We assume that I have the power set of x's already computed. What's left to do?
Add the x on its own list to the lists of lists.
So I have to take x and I have to like attach it to every thing in the power set. But also do what?
Add it on its own.
Well, no, I don't have to add it on its own because like the empty set is going to be back in that. I'm going to concatenate x with the empty set in the power set. Does x have to be a member of everything in the power set? No. So I have to add x to every member of the power set, but also do what? Just have the power set without x's. So how can I do that? So power set of x cons x's. So let y's equal the power set of the rest. And I'm saying it's the power set of the rest. And I add to that, I concatenate just cons x with every member from that power set. And that's going to do the trick. Right, so this is very similar to sort of your permutation. A little bit more simple, but very, I think I actually gave this last year as like their homework question. And they were equally flummoxed. Right, so don't think, oh, I could have got this one. Okay, quick sort. So let's just quick sort, yeah, list of elements. So what should the type here be? Okay, I'm actually going to program this one because it's fun. So a quick sort. So what am I going to quick sort? Oh, well, just hold tight and you'll see. Right? Huh? Right, so I need an ordered type A, right? And then I can take a list of A, and then I want to return A. So okay, when you hear quick sort, just think sort. How can I sort a function? But we're going to do it in a sort of divide and conquer way. Okay, delineate base cases, or edge cases. So what's the edge here? Okay, so how can I sort the empty list? Okay, so delineate general case. So I want to quick sort this. All right, this is a little bit more complicated than, yeah, I want to quick sort this. How do I do it?
So you put, I would have, you get like X, and then you put it in sort of the list, depending on.
No, we're not inserting into a list. We don't do that in this paradigm. Yeah.
You're recalling with the.
Yeah, we get to call quicksort. Okay, so we're going to call quicksort on something. In fact, we're going to call quicksort twice on two different things. What do I have to call them on? So who remembers what quicksort does? Yes?
So don't you want to use, I forget what it's called, but the one that's the list?
Comprehension, yeah? So can anyone define, do you remember what quicksort is?
You have like a pivot, and then you split based on pivot.
Yeah, so you pick a pivot. So my pivot's going to be X, the head. Okay, maybe I'm just going to type it out, and then we can talk about it.
So we're just using x, the head of the list, as a pivot then?
Yeah, X, the head of the list is going to be the pivot, because you said I could choose any element in the list as a pivot. So I'm going to choose the head as a pivot, because it's right there. I'm going to access it. Okay, but then we need two other lists. What other lists do we need? Exactly. I need to know what elements, yeah, X draws from X's, and then where X has to be, oh, I'm doing this wrong, sorry. I need to take it's Y's gets from Y's, such that Y, I guess, is bigger than X. Did I do this comprehension correctly? Right, sorry, yeah, Python yesterday, so Haskell today. I was coding in Haskell in my Python course yesterday, and my kids nearly shit themselves. Well, you could imagine how shocking that would be, right? When you see, okay, so this is everything like all elements less than X, so we need all elements. Did I do greater than? Oh, yes, sorry. All elements greater than X. All elements less than X, so just need to change this, and I'll just do this. Okay, so now I have, oh, why do I have guards here? Pardon me? Oh, Z. And is this correct? Z such that Z is drawn from X and Z is less than X. Okay, so I have all the things that are bigger than X. I have all the things that are less than X. So, and I can quick sort. So what should I do? Some magic brackets. I could. Do you want me to do dollar signs? No? Okay, so this would be like this, I guess. Called like that. Like, it would be this. I think it's that, yeah? Load foo. Okay. Quick sort. Ta-da! So this is always like one of the fun examples to do with new Haskell programmers. It's like, look, I did quick sort in like a line, right? Because like really I could just take these out and put them there. The wheres are sort of not really lines. It's just a way of sort of simplifying our expressions. But yeah.
Could you explain what quick sort does now?
This. No, but I'm being serious though. Like what?
What's the head of the, what's a pivot? Sorry, I didn't get that.
Well, read through the code, right? I'm saying get all the elements that are less than the head of the list, get all the elements that are bigger than the list, quick sort those, and then reconstruct it like this.
Oh, this won't work with any duplicate elements.
Oh, well, okay. I suppose I can just do that, right? Was there another question from this? Oh, thanks, mate. Yeah, so thanks for seeing that. Well, actually, let's see. What would have happened if I would have... Oh, yeah, that probably would have removed duplicates. Yeah, that would have been a hard bug to track. So quick sort is just like a divide and conquer method on sorting. Right? You just choose any member from the list, and then you break the list into two pieces. All the elements that are bigger than that thing that you picked, and all the elements that are less. And then you quick sort those, and then you...
Ascending order, like sorting.
Well, sure, I could sort the other direction if you want.
But then all of it changes.
Yeah, I just have to permute, like then I put quick sort Zs on the right-hand side instead of the left.
Okay.
So like this is, so I'll go back to the old. Like this line is placing X in its appropriate position. Like that's sort of the magic of quick sort. Like this is how things are getting placed, right? Because like I'm not saying X is going into this index. I'm saying X is going to live here and it's going to have neighbors these lists. Right? So this is a placement. Right? This is how you have to see it. Like in Hanoi, right? The
Imperative that instead of making new lists and joining straight with them, you swap them on each side of it. So then there's also, you did everything kind of like with the bar, so there's
Anyways, it's usually the first example of a log complexity algorithm for sorting that we show students. Because all the other ones are sort of quadratic, right, where you have to do these little pivots. Now, I don't think, like, if you were to program this in Python or something, it's not going to be very fast because of, like, you're duplicating tons of lists. There's a more complicated version of this where you can do quick sort in place. Like, yes, but I think it's probably going to be ugly because it's going to be, well, I would just write a function that is going to abstract away the indexing for me is probably how I would handle that. But that's good to think about. Okay, more questions. I'm just going to fill to the very end. Find the least integer in a list of ints. What is the type? Yeah, list of int to int. What are the edge cases? Okay, empty list. Unspecified. General case. X's. Okay. What's the edge case? What should we set it to? Okay, it's not obvious, so we're going to set it aside. And let's just look at our induction and then maybe try to work out what the edge case needs to be. So list min of x cons x's. That's going to be something like this. It's just the minimum of x and what the minimum element of x is going to be. Okay, so now let's try to backwards work out what the base case should be. So here's the edge case. So the minimum element of a singleton list is obviously just the one member of that list. But that has to equal, according to my definition at line 6, x that has to be equal to the minimum of x and the list min of empty. So what should the list min of empty be so that it's guaranteed that x is the smaller thing? Wrong way. Positive infinity, right? Okay, how do we have infinity? So integer actually is an instance of the bounded class. Yeah. Yeah. Yes, I make typos. I'll correct that, but thanks. No, like keep telling me about my typos. I have to correct them.
There's also a brace missing line 1.
Oh yes, I'll fix that too. Anyways, okay, so I'm saying that integers is a bounded type. Oh, it's an added brace. Okay, back to the task at hand, right? Jesus Christ. Integer is a bounded type. Therefore, it's going to provide us a largest element and a smallest element, which basically act as positive and negative infinity. So here I say the list min of the empty set is equal to the max bound of the integers. So any bounded type is going to give you access to max bound. You just have to cast it like this. I'm saying I want the max bound for integer. So keep that in mind. I love giving this type of question on an exam. Right, here's a bounded type. Find me its minimum element or something like that. Or if I were to ask you to do this with a fold, like on your exam, write me a function that uses a fold to find the minimum element of the list. You're going to have to put something in for your base case, right? And the base case is going to be one of these bounds. Okay, we got some time left. So determine if a list of integers contains a sublist that sums to some target. Right, so I have 1, 2, 3, 4, but like I want to show you that like these problems that seem like holy crap, like that seems difficult, become totally trivial if you're able to think inductively about these problems. That's like the skill set I'm trying to give you guys. These are going to make your interview questions like hysterically easy when you go out and Google, because they never expect interviewers to give the dynamic programming solutions to the problems that they're giving. And often the ones that you're given at Google and Twitter, they're trying to confound you with like, oh, you forgot about these like dozen edge cases. And it's like, well, actually, if I use clever things like max bound and min bound, it abstracts, like it gets handled automatically, right? So this is a really powerful tool for you. So just keep that in mind. So determine if a list of integers contains a sublist that sums to some target. So 1, 2, 3, I can make 1, 2, 3. I can make 5. I can make 4, and I can make 0 by choosing none of them. Okay, so what is the type for this? It's list of int to int, isn't it? Oh, it depends. Okay, so it's list of int, the target, and bool, right? Right, so given a list of integers and a target, I want to say if it's possible to make that target with this list of integers. What are the edges? That's one of them. Remember, this is two inputs, so there's going to be like and 0. Okay, so I need to know, right, what it means to make can I make it the sublist sum of the empty list of 0? Can I make the sublist sum of empty on something that's non-zero? So this is sort of obvious, right? I can make the sum 0 from an empty list. So this would be true. And if I can't make anything that's non-zero here, so that's going to be false. General case. That's just like something like this, right? Like x con x's in k. Okay, so the edges, is that just a duplicate slide? Or maybe I'm saying, okay, this is maybe be unclear, but it should be true and false. So how can we determine if we can make a target? Like, what's the recursion here? So it's something like sublist sum, integer to bool. And I know that subsum of empty and 0 has to be true. Sublist of empty and anything else is going to be false. So, yep. No. Just, it's any of, yeah, just go through every position and say keep or not keep. Well, no, I'm not saying they have to be adjacent. So maybe I should say subsequence then of the list, if you prefer that. Okay, I meant subsequence then. Okay, so here's the general case, subsum xcon x's, and here's my target, k. All right, here's the target. So how can I solve this? So what are the two ways that I can do like that will resolve this? Yeah.
Do the subsum on the x's.
Okay, sure, we can do that. So I'll just give you access to where I guess this is going to be a bool. So I'll just say A is equal to subsum of x's in target. Or sorry, target, oh no, x's in target. So this basically says I can do this with the rest of the list, forgetting about this. So maybe here this is going to be like A, but there's another condition where I can also make the target.
A plus x.
I can make the sublist sum in x's of the target minus x. So I can either include x in the sum or not. So if I don't include it, I should be able to make the target in the rest of the list. If I do include it, I have to make the target minus x in the rest of the list. So it's just like this, A or B. Right, so not that complicated after all. Is your mind blown? Oh, wow, okay. So there you go. That's how you would, it's one-line solution, right? So I can either make the sublist sum in x's with with x less than k, or I can make the sublist sum in x's with k. So I'm glad your mind is blown, because like you can now look at harder problems and be like, maybe there's like a really simple inductive solution to this problem, right? Whereas there may not be an easy imperative solution. And I'm trying to give you problems that like fit this paradigm, because like things like bit rating is not a natural fit. Right? That was something deliberately given to you to struggle, to say I could do this in like 2 minutes in the imperative approach. Okay, unfortunately I don't have the, I have a solution for this one, but maybe you can work it at home. So I give you two lists, and then, so you know what a subsequence of a list is? So like a subsequence is you go through each list element and you either decide to keep it or exclude it. If I give you two lists, I want you to find the longest common subsequence of those two lists. This is usually a problem I give to my hotshot Python programmers in my first year class, right? Because it's impossible, like they won't do it without recursion. It just won't be possible. So is that sufficient for, like, ask me questions now, because I'm going to have you do it for homework. Find the longest common subsequence of two lists, okay? Given a string, find all possible palindromic partitions of the string. For instance, if I give you NITIN, if I were to cat this list together, you get the original input, and each of these individual components are palindromes. Same for this, same for that. Given a sequence, a list of integers, find all subsequences that begin and end with the same number. Right, so 1, 2, 3, 1 is a subsequence that begins and ends with the same number. 1, 3, 1 is a... does this have to be continuous? It seems. 2, 2. Okay, so this, I think I just permuted subsequences and sublists in this lecture. So that should be sublist, not subsequence. Right, so find all continuous sublists that end and begin in the same thing. And each of these should be easy, provided you think about it inductively. Yes?
Maybe this is a silly question, but with the first one, do the subsequences have to be like sequential?
Yeah.
In order or something like that?
Like they have to be in the same order that you would find them in the list, but you don't have to, like you can exclude, so like 1, 2, 3 has a sublist 1, 3, right? So again, just go through the list and either say I'm keeping it or I'm excluding it. So there should be, for a list of length n, there should be 2 to the power of n different subsequences, which is why a greedy approach is going to fail, right? Because you're going to have to search through like a search space that's exponential. So give these and like use the philosophy that like I gave you today to try to solve them. And I hope that you'll start, like, after you get comfortable thinking inductively, the problems that I'm trying to give you that should be easy will like be easy then. Okay? So Friday your homework is due. Then you have a week off. Next week I'm going to give you like the next one. But yeah, just try to take it easy a little bit. And then in next week's tutorial you'll be given some tail recursive stuff to work through. Okay. Thanks guys. And hopefully you'll feel a little bit better next week. Okay, bye chat. Thanks for showing up today.